Finished version 1.1 of the GPS CPU frequency standard generator. Getting ready to send the specifications off to China to manufacture the PCB boards, printed circuit boards, and we'll build prototype version 2, which could well be the last one. It came out to be a pretty good project. 1.0 is a perfectly workable version. I just added a few improvements that we'll go through just for the fun of it and to play around with KICAD, the program that I use to do all of the design work. Very neat program, and I'm just learning how to use it. So without further ado, we'll run through the updates, the changes, and a few of the features of that magnificent little program. Here we go. I made a few changes to the dual CPU GPS locked frequency standard generator. So we're now up to version 1.1. 1.0, our original version, works fine, but I've added a few convenient features, and we'll go through them here briefly. And we'll get this thing off to our printed circuit board manufacturers in China, JLPCB. Zero in on the power supply circuit. I've added a non-off switch for obvious reasons. So we're powered externally through this jack J1, which is usually a 9-volt power supply, one of those wall wart thingies. Could be anywhere from 7 actually to 24, 25 volts, and it would work fine with our 7805 voltage regulator. We've got a diode in the circuit just to make sure we have the polarity right on our input power supply. This has to be positive, and this one is negative, or the circuit won't work at all. This diode will stop any current flow. But if it's right, if it's the correct polarity, the diode acts like it's not even there, except for a little teeny tiny voltage drop, which we don't care on the 9-volt supply anyway. These are filter capacitors. Give us as pure direct current power as we can get here. It feeds the, I'm going to say 9 volts at this point, to the input of our voltage regulator IC, the 78L05, and that will reduce it to 5 volts on the output side, which is what we need to power our devices. Our circuit is all designed with 5-volt devices. Here we have we take off the 9-volt power, run it through a voltage divider, and run up to IC Master CPU 1, the Atmega 328 Master CPU. Then we can measure that voltage to just kind of watch the battery voltage. If it gets below 7 volts or 8 volts, then it's not going to really power this very well. So we have a means to watch that. It will display that on our LCD readout. Over here, we've still got the same basic circuit. Remember, our master CPU is the main job is to run the keyboard, which is right here. That keyboard allows us to enter new frequencies into the system, so we can operate. Actually, it runs very well on frequencies from 1 to about 12 megahertz, 12 million cycles per second. But all in all, it's very accurate. It's locked to the GPS signals, like we say, and those are atomic clocks that are actually locked also to the national standard. I believe in Fort Collins, Colorado, is where the master atomic clock resides for our National Bureau of Standards. But that's not really relevant to what we're doing here. It just gives us a very, very accurate signal. It's the idea. This is our LCD display. The master's in charge of running that, where it displays the frequency that we're generating, how many satellites we're tracking, what the battery voltage is, and lock-unlock indicator, which is fairly important depending on what we're using the generator for. If it's locked, then our generator frequency is very, 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 very accurate. If it's not locked, then we're dependent upon the unlocked crystal frequency only of the CPU itself, and that's still very accurate, but it's not as accurate as when we're phase locked or locked to the satellites. That's for sure. Now over here is the slave CPU, And all it does is continually pull the GPS. The GPS, which is hitched in up here, sends out what we call streaming data. It doesn't care whether anybody's on the other end to listen to it or not. It just blasts out the information every second as it receives it, gets it ready to go from the satellites. So you better be ready for it, otherwise you're going to miss some of it. That's why we have this CPU dedicated to doing actually nothing else but listen to this 9600 baud information, which is very fast coming down from the satellite. It just sits and reads it, keeps watching for specific records that'll tell it how many satellites it's listening to, and it has on its through its receiver's passband. It receives multiple satellites at once. Of course, I'm not sure a lot of people are aware of that, but they're pretty fancy little units, those GPS modules. So it's receiving a bunch of satellites, comparing them to figure out not only where it's at, what the longitude, latitude is, but exact time reference. And that information is very valuable to us. We get the lock status, whether it's locked or not locked, to enough of the satellites. It takes usually 3 at least in order to get a good stable frequency lock. And it'll also tell us whether we're locked or not locked. It's all nice to know. We'll display that on the LCD. Anytime the lock status or the number of satellite status changes, the slave will interrupt, send just a brief little bam interrupt signal over to the master. The master will detect it and say, okay, the slave has got something to send me, let's go get it. Boom, it'll come back over, pick up the information really fast over this line right here. Then it goes back to what it was doing, and the slave is free to just continue listening to the satellites through the GPS. So that's pretty cool. It works pretty nice. This is what we call polling. It's just sitting here constantly reading the GPS unit. Say, you got anything to send me? No, I don't. You got anything to send me? Yeah, I do. Bam, here it comes. So that's how that works. It's full-time busy. It doesn't have time to do anything else. So that's why we're using the dual CPU unit. Then the output of our frequency generator is going directly to, and this input signal comes from our GPS itself. It's going directly to a 74 AC14 configured as a Schmidt trigger. The object here is to clean the waveform up as well as we can into a more or less perfect square wave. It's not going to be perfect, but it's going to be close. And at least it's close enough to do the kind of measurement things we want to do. We're interested not so much in how pure the waveform is at this point. But we'd like to have it nice and clean as we can to keep spurious signals out of it. What we're interested in is the actual frequency of that wave. That's the quantity that we're looking for, because we're going to use that to calibrate all of the other equipment that is frequency calibrated in our lab and on our amateur radio equipment. So it's pretty important. Now that we have that finished, down here we have a little explanation of what each of the U-Blocks modules, those are the GPS modules, of what each of them do. And once we've developed the circuit here in the schematic, we send it over to lay out our circuit board. All this with KICAD, a beautiful program, which is free, by the way. It's available to anybody who wants to use it. Take the time to learn it, to use it. And I'm just learning actually to use it now. So that's part of the process here. I wanted to do some of these projects so I could learn more about KICAD. It's a pretty sophisticated, far-reaching program. And I'm just getting a start. I've got a long ways to go to be anywhere near proficient at it. But since I don't make a living at it anymore, I'll take my time. I don't really care. It's just interesting. Here you see we added our LED down here. That comes over from the schematic, and we have to look up the parts in our parts tables and put them on here. Well, looking at which parts we're going to use, the exact specifications for them. Right here will be our slide switch. And our LED, power on LED. We've also added Since version 1.0, we've added the dual socket here for our GPS. So some of the GPSs I've got in my parts drawers here have got the pins for the external connections going down from the board. Some others have them going down from the top of the board. So rather than try to make allowances to run the bulk of the board out this way and that way, I just put in a reverse socket so either board can be plugged in here, and then it'll reach out into this area. I didn't want it to go back over that area because I want to get close to this edge so I can get the antenna input over here. When that board is on there, as you see in the current version, the SMA connector will slide kind of off to the right here, just like the output SMA connector slides off down here. So that way all of our antenna and the antenna input and the frequency output will be on the same side of the board. Make it a little easier to put it in a cabinet, I think. And now note that our keyboard, these are sockets right here for the keyboard and up here for the LCD. So they can either be mounted on the board with the pins directly on the board, plugged in, or they can be, you can fashion a little cable and put them elsewhere on the, like a front panel of a instrument and use them that way. It's whatever you want to build for the enclosure, if you even want to build an enclosure. You notice on the test system that or version 1.0, which was also our test system, we just plugged both the keyboard and the LCD readout into the board itself. Made it a little simpler. These sockets right here, two of them, there's one there, there's one down here. Those are the flashing sockets, programming sockets. Rather than add the circuitry on the board for the USB to TTL converter, they're in a separate offline board. We'll put a socket, two sockets on here. We can just plug those in then to program or flash these CPUs if we have changes to the program. Once that program's up solid and stable, it's not going to change much. They call that the microcode in a lot of cases, and we've already developed that. So once we've developed that, when we've built the board, all we have to do is plug our TTL, USB to TTL circuit in here, flash the memory on it, then plug it in over here, flash that memory, take them off, and we're good to go. We've also added a reset switch. The reset switch will reset the master CPU. Otherwise, you got to disconnect the power. That's what I did on version 1.0. It got to be a pain in the tail after a while, so I added the reset switch. Now, I don't have to reset the slave CPU because the program and the master, once the program starts, it automatically does a reset of the slave. So that's already taken care of. And let's see. We've got everything else pretty well rigged up. I think we're about ready to send it in. Now we'll take a look at the 3D version, also with KICAD, to see what the actual board will look like when we get it back. This is one of the really cool features of this program, I think. We'll go over here, we'll hit 3D viewer. Takes it a second to flash it up. There we go. That's what the actual board is going to look like when we get it back and we get our parts stuffed in there. Here's the capacitors, the LED, the sounder, a little button. This little button sounder will give me a key click. When I hit the key, I like to hear positive feedback with a click. So every time you hit the click, it's going to go click, 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 click like that. And maybe you'll see that when we do the version 1.0. It'll be the same. The other thing I do with that sounder is at the very beginning, when we've reset it or when it starts up, the master CPU will play a little ditty that'll be very familiar to everybody in Nebraska. It's the first line of the University of Nebraska fight song. There is no place like Nebraska. That's just a little added thing in there that I thought was kind of funny. I know I have a weird sense of humor, but there you have it. And here we've got all of this screen printing, which is identifies a very nice feature. Identifies all of the parts that are on there. If we want to work on this or play with it when we're finished, which we often do, if something breaks or goes wrong, it's nice to have everything as identifiable as you can get it. You know which LED this is. These numbers trace right back to the numbers and letters. Parts identification trace right back to the very beginning, to the beginning schematic. Makes it pretty easy to work on this stuff. In fact, is 90% of the problem. I've had to work on boards where I don't have the schematic, and let me tell you, the first thing you have to do is sit down, work out what's going on, hand draw the schematic. Some circuits are readily identifiable. You see them so often. This power circuit, there's nothing very original there, nothing at all. Schmidt trigger is kind of the same. They're like just little bits of manufacturing modules you can store back in your memory, and you recognize them when you see them because you run across them so often. The CPUs themselves, these things are just they're fantastic, absolutely amazing. Unless you've worked in the computer industry for almost 60 years, like I have, both professionally and as a hobby, it's hard to appreciate what these little babies do. But we used to have rooms full of equipment that could barely do what these things will do. So it's just all relative, I guess. All relative. So we can move this around, take a look at, let's look at the bottom, turn it around so we've got it. This is cool. So we can see, I also like to put the legends on the bottom so I know what parts are where. Because if you're going to troubleshoot this thing, you're going to be doing a lot of probing on the bottom of the board typically. And this way I know where everything's at. I don't have to keep referring back to the CPU. I know this is C11, a 0.1 capacitor, 0.1 microfarad. C13 is a 0.1 microfarad or 100 nanofarads. That can be marked all sorts of different ways. 104 would be some of the disk capacitors would be marked with that. Anyway, there's our plug-in outline of our plug-in power supply. That pretty well does it. Now we'll take a look at version 1.0 running along over here. Might tie this all together for you. Here's version 1.0 prototype board, which is run very well. You can see right here's our LCD, which is mounted right on the board itself. And the same way with the keyboard down here. You just saw that one red light blink there. You notice we have 3 satellites locked right now. Our antenna is on a tripod over here off to the right. This is our GPS unit, and whenever we're unlocked, that red light will flash to let us know that our frequency is not exactly locked at that point. If we're calibrating equipment, we want to know that, because if we're doing some serious calibration on a piece of equipment that we really rely on, we want to make sure it's locked. So the flashing light is a little extra indicator to tell us when we're unlocked. Right now we're receiving 4 satellites. The way we're set up with our antenna, we're nowhere near the window so we can see the sky. We're kind of getting reflected signals all over the place here in the dungeon, but it does work. They're pretty cool little LNAs, they call them, low noise amplifiers, and it's picking those signals up even though we're not directly in the sight of some of them. Oh, it's a little marginal because we're not outside. You can tell that we're generating right now 5 kilohertz signal, 5,000 cycles per second, or megahertz. They don't use cycles per second anymore, just us old timers. They changed that to megahertz many years ago now. And our battery voltage is 8.5 volts. That's really not the battery though. We're plugged into a 9-volt supply down here in our input power jack. And here's our keyboard. We talked about the click a little earlier. We're going to enter a new frequency. We hit the asterisk first. If you listen close, you'll hear the slight click. And we'll enter Let's do 10 megahertz. 1, 2, 3, 2, 3, 10 million cycles per second. And the asterisk ends the entry. You can see up there on the LCD it says new value, 10 million. Poke that thing, we're now at, I could stay up there, 10 megahertz is our generated signal. We're locked on 3 satellites. We've been jacking around with this board for a few minutes, and it kind of lost a little of its sync because we had 5, 6, and 7 satellites earlier. And the output signal is coming out right down here. We don't have her on the scope right now, but trust me, it's coming out of there as a nice square wave. So that's how she works when you finish. You can see the parts all mounted in there just like on our 3D view. There's the 7805 voltage regulator, filter caps, input our diodes that give us the right polarity, whether we come in directly on the 5-volt line or over the 9-volt line. Either way, it doesn't care. Our 2 CPUs are halfway hidden underneath the LCD readout. Here's one of our flashing sockets for the master. The other one is under the LCD to flash the slave. So that's pretty much what she's going to look like. Now we could, of course, mount that LCD and the keyboard off somewhere else if we wanted to. But the interesting thing about this module right here is that it's got its own computer built into it, and it's a fast, fancy little machine. That's the guy who does all the satellite stuff. Knows where the satellites are, has the tables to differentiate between them, to know which satellite is which. Very sophisticated, by a company called U-Blox, U-B-L-O-X. And these things are come in different versions. This is a version 7. Over here in our test drawer, in our parts bin, we got a mess of others, 6, 7s, and 8s. And, we use them all for different purposes. 7 seems to be the only one who likes to generate these weird frequencies. Some of the other ones don't work as well for that. So version 7 is the way I'm going on this. And that pretty well sums it up. That's what we've got now, and pretty soon we'll get our boards back. Oh, here's the original board. I use that to kind of take a look at some of the changes I want to make, so I can see it on the original board. This is how they come back from China with the screen, silkscreen printing on them. On this one, I didn't silkscreen the back. I knew it was a prototype. I wasn't that interested in silkscreening the back side, but it gives you an idea. And I've got him upside down there, but here we are right side up. Once we stick the parts on there, we'd have another prototype. They send us 5 is a minimum order, so I still got 4 of these boards laying around. I hate to throw them away, they're so pretty, but I'll get 5 more on my next order of the 1.1s. Anyway, I love KICAD. Cool stuff, cool stuff. Best hobby in the world, right? Outside of AM radio itself. Sayonara.